with what we talked about last week. So we're going to start today talking about glycolysis. One of the things that I think I mentioned last week that what I want you guys to know about glycolysis, I'm going to throw some pathways up, doing some things, but what I want you guys to know is what goes in, okay, and what comes out of each pathway. And then I want you to know if there are enzymes that regulate the speed of the pathway, that are key for driving the pathway. I want you to know those particular enzymes and what step where those things happen. So I will point that out, okay? But I'm going to show you in the next couple of slides, I'm going to show you all of the steps in glycolysis. It's not biochemistry. You don't have to memorize them. You don't have to know the molecular structure of all of those things. I'm still scarred 25 years later from all of that, but I want you to know what goes in and what comes out and where it's regulated, okay? I have some lovely questions on your worksheet that ask just about that. So, glycolysis is a pathway whereby glucose goes in, okay, and we make lactic acid, and we couple that with making ATP, okay, with making ATP. It is a process that has, depending upon where you cut it off, 12 or 13 steps, okay? Because it has more steps, it's much, much slower than the creatine phosphate pathway, than the myokinase pathway, right, which are one-step reactions. So it's much slower. Going all the way to making lactic acid allows us to keep the process going. I'll show you why and how in a couple of slides. But it also produces hydrogen. Okay, lactic acid is an acid. It makes the intracellular environment more acidic, and that causes problems. Okay, so going from glucose to lactic acid gets us double or triple the energy, as you guys will see, as we get from creatine phosphate. So we get a lot more energy than we would otherwise. But it's slower, and within a couple of minutes, if that's the predominant pathway, we're going to make too much lactic acid. It's going to shut everything down. Okay, so it's a trade-off. It's a trade-off. Okay, remember, it occurs in the cytoplasm of skeletal muscle. This will be really, really important because one of the things that we make at the end, it can go to lactic acid, or it can go into the Krebs cycle, which means it has to get into the mitochondria. So this is in the cytoplasm. If glucose is our substrate, that glucose is primarily going to come from one of two places, and where it comes from really matters because it alters the amount of ATP we make from it. Okay? If we have a glucose molecule that goes into glycolysis that has come from glucose that's in your blood, okay? That means it's glucose from something you ate. It's glucose from glycogen in your liver that was broken down, right, to try to elevate and maintain blood glucose levels. Or it's from a non-glucose precursor like protein that's come from the liver in gluconeogenesis. So if it's come out of the blood, we make 2 ATP. Okay, 2. If it comes from muscle glycogen, we make 3. And I'll show you guys why in the next couple of slides. Okay, but where the glucose comes from determines, are we getting double or triple the energy yield that we get from creatine phosphate or from myokinase. Okay? It's faster than the aerobic pathways, primarily because there's fewer steps, and we have to run this to get substrate to go into the aerobic pathways sometimes. Okay? So it's slower, but we get what's called end product inhibition. We make hydrogen from lactic acid in inhibits things. Okay? All right. That's where we are. So the next slide, okay, demonstrates where and how this 2 versus 3 ATP yield comes from. Okay, what you see in the blue is inside of a muscle fiber. Okay, you've got glycogen in the muscle. Okay, glycogen in the muscle, which gets to skip this glucose 6-phosphate step, which I'll show you in the big pathway in the next slide. Okay. And so it doesn't cost us any additional energy to go from glycogen right into sort of directly into glucose 6-phosphate. If you've got glucose coming from the blood, the first thing that we do when it enters into the muscle cells, we take an ATP molecule, we use an enzyme, called hexokinase. Had a brain fart for a moment. An enzyme called hexokinase that breaks down ATP and hooks a phosphate onto the glucose, which gets us glucose 6-phosphate. We have to do this to blood glucose because adding that phosphate traps it in the cell. If you don't add the phosphate, it can just turn around and go right back out of the cell, right? You come in the door and you're like, whoops, nope, don't like this. I'm going right back out. Okay, that's what happens. So it costs us an extra ATP molecule to trap that in the cell. And the muscle glycogen, when it gets broken down, it gets to skip that step. Okay. Here's a thing from a textbook that's older than all of you guys. This is from my biochemistry book from when I was an undergrad. This is what's called the Embden-Meyerhof pathway. This is all of glycolysis except turning pyruvate into lactic acid. Okay. I like to approach glycolysis like this because this pyruvate here at the end can be made into lactic acid. Okay. Or that pyruvate can move into the mitochondria and go into the Krebs cycle. And so in some ways, this part of the pathway is identical no matter the fate of pyruvate. And it's the fate of pyruvate that determines, are we making lactic acid, or are we making a whole shit ton of energy in the Krebs cycle and the electron transport chain. Okay? All I want you all to know on this right here, which is what Todd has in his summary has broken down for you, is glucose goes in. So you see glucose at the top. Okay? Glucose from the blood, there's an enzyme at number 1 there called hexokinase that takes an ATP molecule, grabs a phosphate, sticks it on the glucose. Now we'll do some organic chemistry. We have glucose 6-phosphate. Okay, there we go. If you break down muscle glycogen, then it comes out of the glycogen as glucose 6-phosphate and it enters right there. Okay, it enters right there. The next thing that we do is we're going to move down 2 steps. It goes glucose 6-phosphate. We turn the glucose into fructose. There is an enzyme. You don't have to know it, but it's that next step going from fructose 6 to fructose 1,6, bis or biphosphate. Okay. We add another phosphate group on, so it costs us more ATP. You break ATP down, hook another phosphate on. That step right there. That third step is driven by an enzyme, okay, called phosphofructokinase. We abbreviate it as PFK. You need to know hexokinase and you need to know phosphofructokinase. You have to know PFK because this is the slowest step in glycolysis. Okay, that's the slowest step. Because it's the slowest step, that is the rate limiting step in glycolysis. Okay. Glycolysis can only go as fast as PFK allows us to go from fructose 6 to fructose 1,6 biphosphate. Okay. On Wednesday, probably you will see that during exercise, we can do things to that PFK enzyme and make it run faster, which is good. Okay, it's good. Okay, so we get to fructose 1,6, then we split it in half. Glucose and fructose are 6 carbon molecules. We're going to split it in half and have 2 3-carbon molecules. Okay, as that happens, we're going to move our way down, okay? down these pathways. You don't have to know any of the enzymes. You don't have to know any of the actual sort of products we're making at each step. What I do want you to know is that as we go from fructose 1,6, we are going to, on each side with each of our 3 carbon molecules, we're going to steal some electrons. We're going to put electrons on, pull electrons out and put them on an electron carrier called NAD to make NADH. And then we're going to peel off the phosphates off of each of our 3 carbon molecules. And as we peel the phosphates off, we do what's called substrate phosphorylation and we turn ADP back into ATP. So we get to fructose 1,6, we split it, and then as we go down, we're going to make 4 molecules of ATP and 2 molecules of NADH. Okay? And so we arrive at, we're going to net 2 ATP if it's from blood glucose, because I had to put 2 ATPs in, right, to move the glucose down. So if I put 2 in and I make 4, I net 2. If it comes from muscle glycogen, I only have to put 1 in. I put 1 in at the PFK step. I get to skip the first one, so I net 3. I made 4 and I had to put 1 in. Okay? Seems like a lot of work to make not that much ATP. And in fact, that's correct. Okay? But it's infinitely more ATP than we get from creatine kinase and those things. And in theory, as long as you have glucose to feed into the system, okay, or fructose or some kind of carbohydrate molecule, you can run the reaction, okay, for several minutes. Or depending upon what happens at the pyruvate at the very, very end, you can run this reaction indefinitely. You don't make too much lactose. Okay. Questions about all of them? Okay. Glucose goes in. We put 1 or 2 phosphates onto glucose. Okay. PFK is our rate limiter, and then downstream of that, we make 4 ATP and 2 NADH molecules. All right. That's what I want you guys to know. The confusing and conceptually difficult thing is what happens next. Okay, is what happens next. It's what happens to this pyruvate and why that pyruvate either gets turned into lactic acid or it goes into the Krebs cycle. That is the conceptually difficult piece of metabolism that makes all of this tricky to understand and kind of pushes us one way or the other. Okay. Okay. Here is the same thing, okay, but this is from your textbook, right? And it just shows you the same kinds of things, which shows where the ATP goes in. And I like that it had this nice sort of explanation of what is happening at each step on the left, okay? But again, glucose goes in, PFK regulates us at fructose 1,6, and then downstream we make NAD molecules 2, and we make 4 ATP. So we either net 2 or we net 3. Okay. Okay. I have written a thing here on this slide, and it is a lie. Okay, it is a lie, but I think it makes it a little bit conceptually easier to understand. Okay. The key thing about all of your aerobic and anaerobic metabolism realistically is what happens to that pyruvate at the end of glycolysis. Okay. You read some textbooks and it says there is an anaerobic fate of pyruvate. And I do this, I don't like to say that there's anaerobic and aerobic glycolysis because that's a lie. Glycolysis is completely anaerobic. You use no oxygen to make the pyruvate. It's the fate of the pyruvate. So the anaerobic fate of pyruvate is you have pyruvate and you make lactate or you make lactic acid, which then dissociates into lactating hydrogen. Okay? This process is driven by an enzyme called lactate dehydrogenase, or LDH. I need you guys to know that particular enzyme. Okay? By lactate dehydrogenase. It takes the pyruvate and it actually we donate electrons from those NADH molecules back onto the pyruvate, and we make lactic acid. Okay? And that allows glycolysis to continue as a process. Okay? It allows us to free up those electron carriers, and so glycolysis process can continue. Keep making more pyruvate. Okay? This is a perfectly fine and good end point of glycolysis, except if you want to exercise. If this goes on for more than a couple of minutes, you're screwed. Okay? The aerobic fate of pyruvate, okay, is we're going to take pyruvate, we're going to stick it into the mitochondria. So it's gone from being in the cytoplasm into the mitochondria. We make something called acetyl coenzyme A. Acetyl is a 2-carbon molecule, and then the coenzyme A is just a carrier, right? But I'll show you guys when you go to acetyl, we've lost the carbon, which gets made into carbon dioxide, which is why you breathe out carbon dioxide. Okay? When we do this, we steal some more electrons in the mitochondria, and then we stick the acetyl-CoA, or the acetyl group, into the Krebs cycle. And it spins around and around, and we make a whole bunch of, we reduce a whole bunch of NAD to NADH. We grab a bunch of electrons, and then it goes to electron transport chain, we make a shit ton of energy. Okay? This is better. Okay? This is better. Better because you don't make hydrogen. Okay? It inhibits things, and it's better because this process makes 2 or 3 ATP. This process makes 30, 35, or whatever we've decided today that it is. You read a textbook and it's like, it makes 3.5 ATP. No, it doesn't. It makes 2 sometimes, or it makes 3 sometimes, and it makes 4 other times, and it averages out to that. You can't make half an ATP. But this is the better thing. Okay? We will talk about what is it that tips the pyruvate in one direction or another in a few slides. Okay? But that's glycolysis. Glucose in, carb in, put some energy in, make a little bit back, reduce some electron carriers, and then the pyruvate goes to lactic acid, or it goes into Krebs. Okay? I think you can memorize that much for me. Well, do not look like a very confident bunch this morning. Okay? Do we need to give you guys 5 minutes to try to study that, and then we'll squat until somebody gets it right? No, talk about while you're squatting, where's your pyruvate going, right? On all of that. Okay. Okay. I have a slide talking about NAD and FAD, which are these electron carriers that are really important in metabolism. Okay. Their goal is to transport the electrons and then the hydrogen molecule or the proton that follows it, right, into the mitochondria, or to donate them back and allow us to convert. The book calls it pyruvic acid. So in biochemistry, when I say pyruvate, what you're really making is pyruvic acid, but it dissociates into pyruvate. And we say lactic acid, and then it dissociates into lactate. So we use those words interchangeably. Okay. But we have nicotinamide adenine dinucleotide, and then flavin adenine dinucleotide, this FAD molecule, which the FAD we only use in the mitochondria. This is only used in Krebs. But NAD is also used in Krebs and also in glycolysis. Okay. All right. And so what you see here is pyruvate, right, or pyruvic acid on the left. And then you can see the LDH enzyme in the middle. You can see that we are pulling the hydrogens and the electrons back off of NADH using LDH, and that turns the pyruvic acid into lactic acid. So it's basically, we're shifting one of the bonds, and we're putting the hydrogens back on. Okay. And so what we do then is it allows us to move these things around and continue glycolysis. The other possibility is if you're not making lactic acid, is that the hydrogen, the things on these NAD molecules or these NADH molecules get shuttled into the mitochondria, and you can use them then in the electron transport chain to actually make some energy in the electron transport chain. There's a specific shuttle system across the membrane of the mitochondria that does this. We're not going to talk about it. We're not going to talk about what it's called or really how it works very much, but I just want to present it as this is a thing that happens. Okay. Those electrons are going to one place or another. Okay. Now, before we get into aerobic metabolism, we have to talk about something called lactate threshold. Okay. So for this, everybody stand up. Okay. All right, it's Monday. We got to do this. You all want examples, so here we go. Okay. What we're going to do right now. Okay. You guys are all standing here. Okay. Some of you in varying degrees of awakeness, but you're just standing. Okay. We're standing. If I was to do a finger stick on all of you, get a little couple drops of blood. I can measure, and in your blood, there's a certain amount of lactate that has come from the production of lactic acid collectively in all of the muscles in your body. Okay? That number is likely to be under 2 millimoles, which who gives a shit what a millimole is? But just know it's under 2. Okay? It's under 2. Now, okay, rather than squat, we're going to do another fun thing. Arms out. Okay, arms out. Just hold your arms out. Don't hit your neighbor. Okay, don't cheat and hold hands with your neighbor. Just arms out. Okay, as we do this, where has the initial? We've been doing this about 15 seconds. We've used all of our creatine phosphate. It's gone. Okay, now you guys are instantly, even though it's isometric, right? You are turning glucose into pyruvate at a very rapid rate in those shoulder muscles right now. Okay? Turning it into glucose. Turning glucose into pyruvate. Some of that pyruvate is going into the mitochondria. Others of it is going and becoming lactic acid. Okay? As you hold this for a longer and longer period of time, how are our shoulders feeling? Some of y'all are probably like, this is fine. It's not a big deal. Okay? If I wanted to make it worse, I'd make you do this. Flap them like you're a bird, right? Concentric contraction costs us more ATP. But you're holding it. As your muscles begin to burn a little bit, what you are experiencing is you're beginning to make more and more and more lactic acid. Those hydrogen ions are activating, they're called A6 channels, they're acid sensing ion channels, and they result in that burning sensation. If right now I did a finger stick on you and I measured lactate in your blood, it should be higher than what it was at rest. Okay? All right, you guys can sit down. I did that one like 15 years ago in class, and I told everybody that whoever can hold their arms out the longest can have a bonus point on a test. And let me just tell you how long, people were like 20 minutes on things, okay? So it was wild. Okay, so what happens, okay? And this is really important. This is really important. You are always making some lactic acid. Okay, you're always making some. Remember, all the pathways, all the time. You're always making some. Typically, what happens is the amount of lactate in your blood and the amount of hydrogen in your muscles and in your blood is in this balance. Okay, it's a balance of how much we make in the muscles and then how much we can actually remove. Lactate is not the enemy. You make lactate, it gets into your blood, it goes in your blood, and it gets taken out by a different tissue, and you just stick the lactate into the Krebs cycle, and you make energy out. Lactate's not a problem. The hydrogen is a problem. Okay, so lactate threshold represents an exercise intensity. Okay, it's an exercise intensity, so it's an amount of force production at which, okay, the balance of what is happening to the pyruvate begins to get tipped towards making more and more lactic acid. Okay, you need enough ATP fast enough that pyruvate and then all the steps of it going into the Krebs cycle can't keep up with ATP demand. Okay? And so more and more of it starts getting shunted or pushed over into lactic acid. So we can recycle those NADH molecules into NAD and keep running glycolysis. So lactate threshold represents an exercise intensity at which the amount of lactate in your blood begins to exceed what that amount is at rest. Okay, at rest. Anytime you start exercising and you get over lactate threshold, you're likely to feel this. Okay, your breathing is going to disproportionately increase and become heavier and faster. Your muscles are going to begin to burn a little bit from those activation of those A6 channels with the hydrogen ion. Okay? And so that is what this represents to us. It's not all bad because we have this thing called the lactate shuttle where lactate goes out of one muscle fiber into the blood and then it gets pulled into a different muscle or to a different tissue via this shuttle and it goes into the mitochondria and you make energy out of it. So that part's great. Okay? That part's great. But it has some other drawbacks. So for any of you guys, and I don't know that we do this in testing a prescription or if you do it in Dr. Ferrer and Andrea's class, but you can measure what's called lactate threshold. So what you see here is on the y-axis is finger stick measure blood lactate. Okay. On the x-axis is power output on a bike. Okay. You guys had to ride those crappy Monarch bikes to do the VO2 max estimation protocol and principles of health and fitness, right? You did the YMCA protocol. Okay. So just imagine you've got that bike and we're adding more and more kilopounds of weight to it and you're pedaling at the same 50 or 60 reps per minute, power output goes up. Okay. So if you are at rest, blood lactate, I don't know, about 1 or so, and you start exercising, you can imagine slow walk, regular walk, my wife walking, which I call ramming speed in those ways, up to a jog, up to a kind of a brisk jog, you will note that lactate levels in the blood stay relatively constant. You've gone from rest to kind of relatively moderate intensity exercise, and your body is able to handle all of the pyruvate that is being made at the end of glycolysis, and most of it can still go into the Krebs cycle. Okay, so lactate levels are going up very much. You then get to a place where here's the first place where it begins to increase above baseline level. Okay, then if you continue, then it kind of goes up exponentially after all of this. Okay, so this point right here is called lactate threshold. That's the point where a lot of people exercise begins to feel different. Okay, you will notice the sensory changes that are happening there. In relatively untrained people like me, it's probably going to occur somewhere between 45 and 60% of VO2 max. In very, very well-trained aerobically individuals, lactate threshold might be at 90 to 95% of VO2 max. Okay. In my first faculty position, we were a Division II school, and so basically those of us in the department functioned as like the sports scientists for the athletic teams, and we did lactate threshold testing on all of our cross-country runners, and our best female cross-country girl, her VO2 max was not particularly high, but her lactate threshold was at 93% of her max. She could basically run at VO2 max just for a race, which is crazy, right? She was about as good as she could be. but her VO2 max was not super high. It was like, I don't know, it was like 47 or something mLs per kg per minute. But she could race basically at her VO2 max. We had some other girls who had VO2 maxes in the high 50s, and their lactate threshold was only at like 60% or something. And so once you start and you get out to about there, once you get over about 4 millimoles of blood lactate, you exceed something called critical velocity or critical power, and you will, if you maintain that pace, you will fatigue. You will go to VO2 max. There's a zone over lactate threshold for a little ways where you can run and you can actually reach a steady state and maintain this. Okay. So VO2 max matters for aerobic performance, but your lactate threshold as a percentage functionally in some ways determines kind of how close to your maximum potential can you race in those ways. Okay. So that's lactate threshold. Does that make sense? It's an exercise intensity. Okay. It's an exercise intensity. In most of you guys, it's probably between 60 and 80% of your VO2 max. It's somewhere in the neighborhood of a brisk jog is about where your lactate threshold is. Okay. So that's what's happening. That's kind of our tipping point in the midst of these things. Okay. We talk about lactate accumulation. This is a thing that's trying to illustrate the lactate shuttle. Okay. What you have here is a fiber. You're making lactic acid in that fiber. It dissociates the lactate, goes into the blood, into venous blood. It circulates around. It can get taken up by the heart. It gets back into arterial blood. It can get taken up in any other fibers or tissues, and it gets used again. Okay. If you ever see these words, I'm not going to ask you about them on a test, but there's a thing called a monocarboxylate transporter, or an MCT, that governs sort of pulling that lactate out. What I do want you guys to know that will be interesting is in controlling part of your lactate generation, fast twitch muscle fibers have a more active lactate dehydrogenase enzyme than slow twitch fibers. So fast twitch fibers, for any amount of pyruvate that is getting made in a fast twitch fiber, a larger percentage will get made in acid than in a slow twitch fiber. Okay. So when you see this, it's calling this, right, a fast glycolytic fiber or a type 2X fiber. In some ways, if you will, they make a lot of lactic acid. And then here it's getting taken up into a slow oxidative or a type 1 fiber that has more mitochondria. You can take the lactate back into any fiber, but in our controlling of these rates and things, if you've got more type 2 fibers, you're going to make more lactic acid because the LDH enzyme. Okay. Your heart also has LDH. And the heart has the least active LDH ever. Okay. When you have a heart attack and you experience angina, right, that pain that radiates neck, left shoulder, and those things, the heart does not have nociceptors. It doesn't have pain sensing nerves. And so when the heart becomes ischemic, you have no oxygen, you finally begin to make lactic acid in the heart, and that acidity then acts on the nociceptors in the surrounding tissues, and that's why you get that radiating pain. The heart very rarely makes lactic acid. It almost has to have a lack of blood flow in areas before it moves. This LDH enzyme is very, very slow, very inactive. Okay. All right. So that's some of the physiology of all of this. Okay. Okay. We've got a few minutes. We'll introduce aerobic metabolism and how this is going to interact together now. Okay. Aerobic metabolism, depending on where and how you want to start it. Okay. It is not wrong to say aerobic metabolism starts with the glucose that first enters into glycolysis. For aerobic metabolism of carbohydrates, we need glucose to pyruvate, that we then move that pyruvate into the mitochondria. It goes through the Krebs cycle. We steal a bunch of electrons. They go to the electron transport chain, and we make a bunch of ATP. Additionally, aerobic metabolism involves taking free fatty acids out of the blood or from inside your muscle fibers and pulling 2 carbons at a time off of those lipid molecules, of those free fatty acids, and putting those 2 carbons into the Krebs cycle. Okay? So glycolysis can only use carbohydrate. Aerobic metabolism technically can either, you can put a carbohydrate precursor into the Krebs cycle, or you can put a lipid precursor into the Krebs cycle. So aerobic metabolism breaks down both carbs and fat as their substrates. Okay? Both. That will become important on Wednesday. Okay? That will become important. This is the primary ATP generating pathway in your body because it makes so much ATP. Right? Creatine phosphate pathway, you get 1. Glycolysis, you get 2 or 3. For a carbohydrate molecule that goes to pyruvate and then goes in, you're going to make 38 or 39 total ATP. For 1, say 16 carbon free fatty acid molecule, you're going to make like 100, okay, ATP molecules. It's the primary one because it makes so much. Okay. Also, it doesn't make any byproducts that cause problems. Right? It doesn't change the acidity and lead to fatigue and that. It's not a thing where you generally run out of substrate like you do with creatine phosphate. It's not a limited amount. You have enough carbs and fat in your body to allow you to make energy for a month. Okay. Primary thing that limits aerobic metabolism is it's slow. In rare instances, it requires oxygen to operate. The electron transport chain needs oxygen. In rare instances, at high altitudes, in very, very, very high intensity exercise, or in issues where you've got sort of purposeful ischemia, right? The dude's wearing, it's always the dudes, right? The bro's wearing the, I call it the vein mask from Batman, the little thing that like you put it restricts your ability to breathe, and they go and they work out and they're wearing those. They've given themselves COPD, basically, what they've done. They've given themselves a pulmonary disorder, right? That's all they've done, right? So it does not simulate altitude in any way, shape, or form. In any way, shape, or form. You're just giving yourself a pulmonary disease. But you put that on, and you may be in a place where you have a lack of oxygen, right? You cannot provide enough oxygen because you can't breathe correctly in order to maximize those. And it's very, very rare. Okay. Energy generation, if we feed you oxygen and some sort of substrate in this, is basically limitless. Okay. We can put you in a coma and IV drip you some fat and some glucose. As long as you're breathing, you can run this forever. Okay. Until the other tissues in your body give out. Okay. So that part's not limited, but it's slow. It's slow because the carbs have to make it all the way to pyruvate and then through another 12 steps in the mitochondria before you make all that energy. The fat does a similar thing, and so it's slow. And because it's slow, it's hard for us to get all of the energy that we need in high intensity exercise really, really quickly. Okay. So in the first couple of minutes of exercise, if you're doing super high intensity stuff, you can't go long enough because aerobic cannot go fast enough to make enough ATP to actually have you be able to provide an adequate amount. And so you have to make lactic acid, you have to use up your creatine phosphate. And those things will limit us. Okay? All right. This occurs in 3 primary steps, and I apologize, I need to change this. It is not the actyl-CoA, it is acetyl-CoA. But you take the pyruvate from glycolysis, move it into the mitochondria, hook it on to coenzyme A. That's our first step. Then there's the Krebs cycle, and then the products of the Krebs cycle and this intermediate step are going to go to the electron transport chain, and we're going to make a bunch of ATP by passing some electrons and moving some hydrogen. Okay. That's the step that we're going to have in the world. And so because of all of this, again, this is why it's slow. This is why it's slow. Okay. More old pictures. Again, this is from my biochemistry book that is older than you guys. This is the Krebs cycle. It's sometimes called the citric acid cycle. Depending upon kind of what book you read and those things, but you will see at the top, there is pyruvate. Okay. All I want you all to know is pyruvate gets converted into acetyl coenzyme A. That acetyl coenzyme A, the acetyl group gets added onto oxaloacetate, and we make citrate. You don't even have to know oxaloacetate. You don't have to know citrate, but pyruvate has 3 carbons. The acetyl group has 2. Citrate has 6. Oxaloacetate has 4. And so the importance of knowing the carbons is we pull a carbon off of pyruvate, that makes CO2. Citrate has 6 carbons, oxaloacetate has 4. So we lose 2 carbons as we go around. They get made into carbon dioxide. It's the pulling off of the carbons in the Krebs cycle that makes the carbon dioxide that you guys breathe out all the time. That's where this comes from. All right, that's where the CO2 comes from. So pyruvate in, acetyl-CoA into Krebs. That's it. That's all I want you to know. Okay. But you can see again that there is 1, 2, 3, 4, 5, 6, 7, 8. There's 9 steps here. That glucose has already gone through 13 steps to get to pyruvate. It's like a 20-step process, and we haven't even gotten to the electron transport chain. Okay. That's why it's slow. That's why it's slow. Okay. Right here, this enzyme, alpha ketoglutarate dehydrogenase, is the rate limiting enzyme in the Krebs cycle. Okay. The only reason that I know that is that was the final Jeopardy question at a national quiz bowl competition that we had a team that was in about 7 years ago. They were winning going into final Jeopardy, and that was the final Jeopardy question. And our previous chair who taught ex-phys did not teach that. I've never taught it until then, right? Like the Krebs is not a thing. It goes fast enough. The Krebs is never in anywhere in metabolism. Krebs is not limiting anything. It goes fast. But technically, alpha ketoglutarate and succinyl-CoA, this is the slowest step in Krebs. I'm not going to ask you guys this, but I'm just throwing it out there in case I ask any of you guys to ever come be on our quiz bowl team. So we have 2 teams that are going on. So I'm going to be going on. Exactly. We start off at this conference we're at in Fayetteville on Wednesday. So we've got 2 teams that are there. So then you guys that are juniors, you do well, you're going to get a call from me. Right? If you win there, then they pay for you to go to the national. And so our group got to go to we went to San Diego. Yeah, the week in San Diego, paid for it. Just go and get a quiz bowl.
Hey, DB.
Yeah.
I'm pretty sure the rate limiting step as it's listed in the slides is isocitrate.
No, is it isocitrate?
It is.
Shit. Okay, well, see, you can see how important maybe it is. We should check that. Ty, Google that real fast for us.
I'll double.
Maybe I'm wrong and it's isocitrate. It's one of those 2, right? You can see how important that I think it is. Okay, guys, the other big takeaway from all of this in our last couple of minutes here is the thing that we do in the Krebs cycle. We make carbon dioxide, and as we pull those carbons off, we grab electrons. Okay, we grab electrons. When we make 3 molecules of NADH and 1 molecule of FADH. And this is where all those electrons that we need for the electron transport chain are going to come from. Okay. So we make a bunch of these. You don't have to know the steps where we make them or anything else or the actual numbers. Just know you go through Krebs, we make CO2, and we steal electrons.
It's isocitrate.
Okay, sorry, I was wrong. It's isocitrate dehydrogenase. See? So can't expect you guys to know anything that I don't know. In that particular one. Okay, thank you, Ty. This is why Ty is here. Okay. I'm going to mention, I'm not going to ask you a question about it, but it's on the slides. I just want to tell you guys why it's here. If you guys remember way back in like the 2nd week of class, I showed you some muscle fibers that had been stained for fiber type and different things. And one of the things in one of those slides that it was stained for to check mitochondrial content it was stained to this enzyme in the Krebs cycle called succinate dehydrogenase or SDH. So I just bring it back here, that if you ever illustrate, this was one of the things that people would look at to try to determine how many mitochondria are in individual muscle fibers, as you can look for the amount of this SDH enzyme. Why would you stain for that enzyme and not the rate limiting one or one of the other ones? I don't know. Okay, I don't know. It's just because we did. Okay, we will stop here. All right. See you guys on Wednesday. Right. Very good.
I got the exam 2 questions updated as well as exam 3, I published exam 2 questions. And then, yeah, based on all of that.